This is 5.2 logarithmic functions. Logarithmic functions are the inverses of exponential functions. If we have the logarithmic function of log base a of x equals y, that's how this is said, log base a of x equals y, the exponential format would be a to the y equals x. You can convert a logarithmic function into an exponential function and then an exponential function back into a logarithmic function. Now a, the base number, cannot be equal to 1. Let's look at some examples here. If we have the logarithmic function log base 3 of 9 equals 2, to rewrite that in exponential format, that would be 3 squared equals 9. To look at that in the process to get that, your base number is 3. Our exponential number is 2. So 3 to the second power is equal to 9. So let's look at the next one. Log base 2 of 16 equals 4. 2 to the fourth equals 16. 2 to the fourth equals 16. The next one, log base 2 of 1/8 equals negative 3. 2 to the negative 3 equals 1/8. 2 to the negative 3 equals 1/8. On the last one, we have log of 100 equals 2. When there's not a number down here, this is a 10. So 10 squared equals 100. 10 squared equals 100. Okay, so why is that important to understand? Well, if I have log base 3 of 81, I do 3 to what exponent? Because I'm trying to find what does this equal. So 3 to what power, 3 to what exponent, equals 81. And you could think on your head or think on a calculator. Use a calculator by doing 3 times 3 is 9. And 9 times 3 is 27. And 27 times 3 is 81. So how many 3's did I just write down? 1, 2, 3, 4. So this value would be 4, which means log base 3 of 81 is equal to 4. When you're doing logarithmic functions, you're really evaluating what is the exponential function on my base value to get 81. So it's kind of thinking a little bit backwards in a roundabout way to evaluate a logarithmic function. Let's look at some properties of logarithms. If you have log base a of 1, well, to get the 1, I need an exponent of 0 on the a, right? A to the 0 equals 1. That's why this answer is 0. When I have log base a of a, to keep my a, I need an exponent of 1. A to the first is a, which is why the answer here is 1. Log base a of a to the x is equal to x, because that's the exponent that I would need to have to get a to the x. I need a to the x. The exponent is x. My answer, remember I just told you, is the exponential value on your base number. So obviously x. Now let's look at this last one. A to the exponent of log base a of x. Well, if I convert this into a logarithmic function, a to the y equals x is log base a of x equals y. So if I take my a, make that the base number, my x value, the answer, goes next to the logarithmic. So x goes right here. and then the exponent becomes the answer. My exponent was log base a of x, log base a of x. So you can see these are equal. So a to the x, I would have to have x right here, and that's why a to the log base a of x equals x. Another way to think about this is because of exponential functions and logarithmic functions are inverses of each other, these cancel out, and you're left with x equals what? Obviously x. So that's why that works. So if I say a, no, not a. If I say 5 to the log base 5 of 8, the 5 and the log base 5 cancel because those are inverses of each other. And what's left? 8. My answer would be 8. Okay? All right, let's look at some special logarithmic functions. I just mentioned if I have log of x, that's the same thing as log base 10 of x. And if I were to write that as in exponential form, that would be 10 to the y equals x. ln, natural log of x, is log base e. The ln part is the same thing as log base e. So if I have ln of x, I have log base e of x. And to write that in exponential format, if I have ln of x equals y, that's e to the y equals x. Okay, let's look at graphing. Since logarithmic functions are inverses of exponential functions, they reflect across the line of y equals x. This red dashed line is my graph of y equals x. If I am trying to graph log base 4 of x, y equals log base 4 of x, I could do 4 to the y equals x. And this function up here is 4 to the x equals y. So if I had 4 to the x equals y and I had 0, 1, well, log base 4 of x is 1, 0. If I have the 0.14, switch the x and y, I get 4, 1. Okay? The values of the x and y are switched from exponential functions to logarithmic functions. So let's look at graphing one from scratch. To graph a logarithmic function, what I want to do is plug in my values for the y, not the x. So if I take my function here, log base 3 of x, I'm going to convert that to an exponential function. 3 to the y equals x. Because y is now my exponent, that's why I'm plugging in the values for y, because that's going to get my outcome. My outcome is x. So 3 to the negative 2 is 9, because 1 over 3 squared. That negative makes it the reciprocal value. 3 to the negative 1 is 1/3. Why did I put 9 up there? 1/9. 3 to the negative 2 is 1 over 3 squared, which is 1/9. 3 to the negative 1 is 1/3. 3 to the 0, anything to the 0 power, is 1. 3 to the first is 3. 3 squared is 9. Now I have my values here I can graph. 1/9 is very close to 0. Now I go down to the negative 2. I plot my point. 1/3 down to negative 1. 1, 0. 3, 1, and then 9, 2. Okay, so those are my points in my graph, and this is not going to cross the x-axis here or the y-axis here. It's going to run down and continue on forever, essentially right along the y-axis. Let's see how well I can draw this. Okay, let's there we go. We'll clean that up a little bit. Okay, so that is the graph of a logarithmic function, specifically log base 3 of x. Okay, here's some points to take note of. All right, we have this point right here, this point right here, and this point right there. Okay, if I think about just the basics, well, this point is 1/3 -1. This point up here is 1, 0. And then the following point, next point is 3, 1. If I take this and I look at my function, my base value was 3. See the 3 here? -1 gives us the inverse of 3, which is the reciprocal of 3 is 1/3. 1, 0, just like exponential functions always went through 0, 1, logarithmic functions always go through 1, 0 if there's no transformations on it. Okay, so 1, 0 is a standard point for when there's no transformations. And then we have 3, 1. 3 is the base number. 3 to the first is 3. So 1 is your exponent. So if you can kind of remember that, if I have log, whatever the base value is, if I have y equals log base a, I can know these 3 points. And I can think of it that way, where if I have a -1, that's going to give me the reciprocal of my a, 1 over a. If I have a 0, that's going to be 1. If I have a positive 1, 3 to a to the first is a. So you can kind of go through and create these 3 values very quickly, knowing that you start with the inverse for -1. We always go through 1, 0, and then your base value at 1 for 1. Okay? Either way is fine. If this doesn't make any sense to you, what I just told you, don't worry about it. Always use the table if necessary. All right, now let's look at using the transformations to graph. What we want to do is we start with our basic function, whatever it may be. You're going to make your table of values. So you make your table of values, like if I have log base 5 of x plus 2 minus 3. Okay, my basic function would be log base 5 of x. And what I'm going to do is make a table of values for log base 5 of x. Remember, we start with the y's. -2, -1, 0, 1, and 2. 5 to the negative second would be 1/25th. And then 5 to the negative first is 1/5. 5 to the 0 is 1. 5 to the first. And 5 squared is 25. Once I think about these points, then I will apply the transformations that are happening. to plot my points. Let's look through here. I pointed out the transformation values. If I have a negative out in front of the logarithmic function, that is reflecting vertically. If the negative is inside with the x, that is reflecting horizontally. Vertically is up and down. Horizontally is left and right, or side to side. If I am adding a number inside parentheses on the logarithmic function, that is shifting to the left by 5 units. If I have a logarithmic function that is got a minus inside, like -5, that is shifting to the right by 5 units. If I have logarithmic function where I'm just adding 5 and it's not inside parentheses, this would be up 5 units. And if I have minus a number, that is shifting down. So if these are not in parentheses like we had up above, then it's going up and down. Okay, so if we look at this, we have a log base A of x minus h plus k. Remember, logarithmic functions are inverses of exponential functions. So when we think about domain and range and our asymptote, we have to switch our thinking with the x's and y's. With exponential functions, our domain was all real numbers. So if we switch our thinking x and y, that means our range for logarithmic functions is going to be all real numbers. And it is our domain that is affected by the range. Okay? And your domain, because that's your x value that moves left and right, that is going to be x is greater than h. Okay, not the k. Switch your thinking from y over to x. We are affected by the h value because you're talking about x. And we don't have a horizontal asymptote with logarithmic functions. We have a vertical asymptote, which is x equals the value of h. Okay, so this is important information regarding domain and range and asymptote. Okay, let's look at some properties of natural logs. If I have the natural log of 1, that's like taking what you're trying to find what exponent on e will give you 1, and that's going to be 0. Because log base e of 1 is equal to what? E to what exponent? 0. Okay? Natural log of e is 1 because e to the first, e to the 1 power is e. Natural log of e to the x. Well, that would be, I think it's supposed to be x. Let me check here. Yeah, this is supposed to be x right here. X. Let's cross that out. Okay. Natural log of e to the x is x because if I take e to the x to get e to the x, okay? And then e to the natural log of x, just like in the logarithms, these are inverses of each other. And so if you take the natural log or e to the natural log of x, you're going to end up with x. Okay? That's what this explanation is trying to tell you. All right, let's look at this example. If we want to graph log base 3 of x minus 1 parentheses minus 2, we're going to start with our basic log function of log base 3 of x, and then we are going to transform the graph. Now, remember what we talked about domain and range and vertical asymptote. Our range is all real numbers. Our domain is x is greater than the h value. And the h value is -1. Or actually +1 because the formula says x minus h. What value are we subtracting? Positive 1. So you have to think about the opposite of this. So x is greater than 1. And therefore my vertical asymptote is x equals 1. And keep that in mind when we are graphing, because when we are graphing, our vertical asymptote is at positive 1. We are going to use that as a guide. All right, when we plug in negative 2 to the log base 3 of x, we get 3 to the negative 2. That's 1/9. We get 1/3. We already did this example. 1, 3, and 9. And so now we plot our points, or think about these points. 1/9 negative 2 is right here, but I'm going to be shifting this. This is to the right by 1 unit and down 2 units. Okay, so if I'm at that 1/9 and negative 2, I'm going to move right 1 unit and down 2 units. So right here. If I go to 1/3 negative 1, 1/3 negative 1, that's where I would be for log base 3. But now I have to shift that to the right 1 unit and down 2. 1, 0 is right here. Shift that to the right 1 unit and down 2. 3, 1, shift right down 2. And 9, 2, right here. Shift right 1 and down 2. And then we have our graph here. I did a better job on that one. Okay? And your vertical asymptote is here. And so you can see you're going to be guided down. Okay? And that's how I want you to do your shifting so that you're understanding what's happening to the graph. And that's it.